Hello everybody and welcome to the best practices for your machine learning project. This is a lecture as part of the Perception Engineering for Robotics course. My name is Jonas Frey and I'm a PhD student at the lab of Professor Mark Reuter at ETH Zurich. As a motivation for this lecture, I would like to start out by looking at the following picture. So you can see here is the rocket and there's the moon. And here's kind of one of the slogans that I really like. It's kind of ideas are cheap, but execution is everything. So everybody can have the idea of we would like to go to the moon, but then the hard part is actually executing on it and building the rocket that gets you there. And I think the same holds for your machine learning project as well. So with this in mind, I would like to provide you with the tools and share my experience on how I successfully was able to conduct machine learning projects. So before getting started, I would like to pick up on a few questions and problems that recently students came to me throughout this project. So one of the questions that I often hear is, for example, why is my network not training or why is it overfitting? And the answers to these problems are usually that you need to debug and also visualize things. So I will show you how to do these things. Also, for example, at the end of the project, we run into the problem that the results are not reproducible. So I will teach you about the best practices in terms of reproducibility. Next, for example, time management is always a big problem. So the question, for example, at the end of the project is, can we submit the report 2 weeks later? So here a solution again is time management. So I also will say a few words to this. So with this, I give the outline for the lecture now to tell you a little bit of the assumptions that we took. So at first, everything that I will teach you is based on my personal experience. So I supervised over 20 master's student projects throughout my PhD, and I've been working on a lot of machine learning and reinforcement learning projects. I also was able to take this course 3 years ago, so I would like to share a little bit of my experience here. So the assumption for this lecture is basically that you're an intermediate programmer. So you're familiar with Linux and you know your way around the command line interface. If you're an experienced programmer, you have 10 years of experience programming things, this lecture might be not the one for you. Also, if you have no clue about programming and it's the first time using Linux or Python, then maybe this lecture is also not good for you. Everything in between, I try to get you on board and show you a few tricks that maybe enhance your capability to do this project. And then also, just take this into account, is basically make your own decisions. So as said, I don't show you how to code. I will more show you a lot of different recipes that you can make use of. So this lecture should be like a buffet. So take ever what you think is valuable for yourself. So in the end, you have to make the decisions on how you want to conduct your project. So at first, I would like to talk very quickly about organization aspects before we go into the technical details. At the start, here's the project planning aspect to the project. So for example, when you start out with the project, you should create a timeline for yourself. Also, what is very important is communicating your expectations with your supervisors and your partners such that everyone in the project is aligned. And then a few simple questions that you can answer at the beginning of your project is, for example, like, what is the goal of this project? And also, for example, why is this goal relevant or even interesting? So if you know these answers to these questions, you already have a good starting point. Then also what is always important to keep in mind is how can we evaluate progress, how can we measure those things. Okay, then we can just right away jump into the start of the project. So you have talked to your supervisors, you have the project description. So what you need to do at the start is basically doing a literature review. So for this, there's multiple websites that are quite good. So for example, there's Google Scholar, where you can just type in a keyword and then out comes a lot of relevant papers if you are able to type in the correct keywords. Then there's a tool that is called Connected Papers that allows you to visualize based on one paper a graph of the most related works. So here you can see the graph where the color is related to when it's published, so the publishing date, and the size of the blobs are the amounts of citations. So this gives you a really nice connection of how to connect different papers. And then also there's a preprint server called Archive, where usually the latest research is available. Then apart from these websites, you can check out the robotic conferences. So I put down here the most relevant conferences that we're usually submitting to. And also there's something called the proceedings. So there all papers are listed that are accepted for this conference. So these proceedings are usually easily searchable, so you can also type in the keywords there, and then you will find the most relevant research. So by checking out the conference proceedings in the last 1 or 2 years, you can already get a good understanding if someone has tried out what you want to do in your project. Then also there's journals. Journals are usually bigger works, and there's a big variety of journals, and I just put down like 3 very popular ones in the field of robotics. Obviously, we're doing perception and learning for robotics, so a lot of tasks are related to computer vision or machine learning. So again, here I put down the most influential conferences, I would say, but there's many more for you to explore. So just, again, figure out in which domain your project is, and make sure that you find the correct related work. Then, after you have decided which papers you want to read, there's different ways on how you read the papers. And what works is very different from student to student. So I've seen that basically everything works. So one option is, for example, you just highlight the PDF, add some notes inside the PDF. What I like to personally do is just create a Google slide, and then I copy down the most interesting figures, and I write down some own notes, such that I enforce myself to really read the paper and understand. So by writing these summaries, I can ensure that I have given the paper a full read, and I would also recommend you to kind of enforce that you really read the paper and get the most out of it. Then, after you have surveyed a few papers, I think it's also good to keep track of which papers you have read. And for this, again, I've seen everything working. So from like a Google Sheet where you put down the papers, from like Mendeley or Zotero, which are these library management tools or bibliography management tools, but also just having a folder with PDFs or some bookmarks in the browsers work well for various people. So my general recommendation is just choose one and be then consistent throughout the project. And also one aspect that I would highlight is keep reading throughout the project. So you will definitely lose out if you just do a literature review in the first 2 weeks. You should continuously throughout the project keep reading related work, such that at the end of the project you have kind of accumulated a lot of knowledge and you have a really good understanding of the field. So here's again an example of how it looked like for a project that I did with one of my friends in the past. And we just noted down here, for example, the title of the paper, and then we noted down the year when it was published, then from which institution it's published, and if you want to cite it in the end, and then like a small description and then the link to a paper. This allowed us to share information and keep a nice overview. And also we could see the list expand throughout the project, which is kind of nice to have kind of keep track of this. Then let's make a big jump. So now we go from the organization side to a more technical side. So given that we are doing a machine learning project, most likely you will be using Python because that's the go-to language of choice. And at first, when I'm talking about Python, I mean Python 3, given that Python 2 is already deprecated since a few years. So one thing that you can do on your machine is just type in which Python or which Python 3, and then it will tell you which interpreter you're currently using. So you can see here that this is pointing to this user bin Python 3 folder that will basically interpret your Python script. Then there's like different versions on how you can get like different interpreters via virtual environments where we will come later. So then the path might be a different one, and that works for like Conda as well as virtual environments. But this being said, let's have a look at how Python is structured or what you need to know about it. So you have your Python interpreter, which basically interprets your program that you have written. And then there's a Python package management in your environment, which determines which packages you can use. And you can choose from a lot of packages that are already developed by other people for you, where the most famous one might be PyTorch, NumPy, TensorFlow. And there's over 350,000 packages currently available. So you also need to choose wisely. And one of the parts that a lot of students get wrong here is understanding the package management. So I created a few slides for this and try to give you now a gentle introduction into how it works, and if you can't install packages, how to debug it. So the question that was raised by students previously is what actually happens if I install a package. So what you're familiar with is basically that you can use pip install to install a package. So here we are pip installing NumPy, And you can see that we're using pip as a module based on our Python 3 version. So this is basically equivalent to just running pip 3 install numpy. So with this syntax, we can call a module which is pip3. So this is doing the same thing as this other command line. Then, after installing a package, what you can then do, for example, to just check where a package is installed, you can run the following program. You can import numpy as np, and then we can print out the file and the version of it, such that you can see here, for example, on my machine, numpy is installed to the site packages folder under the .local, and we have a version of 1.25. Now I want to explain you a little bit in detail what actually happens in the Python manager itself. So what the Python package manager is doing, you can see on the left you have your file system where you need to install your packages, and on the right you have this Python package index, which is basically a website where developers can upload their packages. And the Python package manager is now responsible for using the internet basically to get those packages onto your local machine and then install them and write them to the correct locations in your file system. So for this, I put down here 3 example paths on where these packages might be installed to, but this is strongly dependent on your system, so you need to check this out on your own. So what is this package manager now doing here in the middle? So the first responsibility of the package manager is to find the most recent package that is compatible for your current system installation, so with all your other packages that you currently have. And also it determines all of the dependencies. So do you need to install or uninstall newer versions of a given package, such that the new package that you want to add can be installed. So as an example, you might want to install NumPy with a given version, and then you need to have Torch with a given version or the other way around. So these specific versions of packages we call distributions, just for you to know also this term. So now what this package manager can be doing is either you can compile a package from scratch, or you can make use of this pre-compiled package formats. And there's namely 2 formats, and you should not be intimidated if you don't understand the details, but everything you can read is with the link at the bottom right here that you can just follow, and it's very easily to figure out what actually happens. So there's wheel or wheels, that is basically a fancy format of zip with a standardized naming on how to zip certain files together, such that you have a Python distribution for it. And they're usually built for a given system, so for example for ARM or for x86, and it's just a packaging standard. And the predecessor to this was basically EGGS, and it's a different build format that is still used today, but not for modern projects anymore. And then, for example, if you have to install a wheel format, what this package manager is doing, there's a 2-stage process where it at first unpacks the package and then spreads it to your local file system. So there it determines which path it has to be copying the files to, and then just puts them into this directory, such that they are later accessible for your Python interpreter. So with this, let's give you a quick overview of 3 different options, how you might manage your packages or which tools you can be using. So per default, you will be using your system Python installation. So that means you just get a new Ubuntu version, you run pip3 install of your package, and that works very simple. Given that we're also doing perception and learning for robotics, it's always good to think about if we can use ROS easily, and that works with the system Python installation. And then the downside of using the system Python installation is that your environment or your setup cannot be easily shared between users, and you will run into version conflicts when you have multiple projects that require different versions, which you will have at some point. So instead, people retrieve using virtual environments. And there's like the 2 options that I put down, is basically using Conda or virtual environment for this. And they allow you to have multiple environments that you can then load or unload, such that you have different versions of Python available, but also different packages that you have installed. And Conda provides you a very quick and reliable solver for your dependencies, and it works across platforms. So it works on Mac OS, but also on Linux. But I assume everybody works here with Linux, so you should not be too dependent on this. The downside is basically that you need to understand that installing ROS is quite difficult for it, and you can make it work, but it's kind of tough. and it's a little bit tricky and unstable. On the other hand, you kind of need to figure out how you work your way around pip and conda, which are both package manager, and it can be a little bit confusing as a beginner. And also one thing to note for conda is that it per default extends your system environment, but by setting the correct flags you can get away with this. For the virtual environment, that's basically the version that I would recommend you to use. It allows for basically the same benefits as conda in terms of having multiple environments that you can load or unload. It also by default extends your system environment and therefore is compatible with ROS in a nice way. So depending on if you need it or not, you can extending your system Python installation can be beneficial or not beneficial. But I will show you some tricks later about this. So my recommendation here at the end of the slide is basically use virtual environments for most cases, especially if you need to use ROS. If you don't need to use ROS at all, conda is also a really good option for your project. So then here is a few tricks that I want to show you. One of the things that make you a good programmer is actually figuring out how to easily get help. So you have your Python package manager pip3, and you can just run the pip3 list command, and then you can see that there's, for example, a lot of different flags that you can be using to get more specific or targeted information. So for example, when you run the pip3 list help, your command line will tell you that there's packages that are installed globally or locally, and also there's packages that are installed for user or non for user. So it's very important to figure out actually how to very easily get information. So a few tricks and tips here. So I talked quickly about this by default extending your system installation. So if you add the following line here, like this export Python user side equals 1 to your bash RC, your Python environment will be always isolated. This requires a little bit more storage, but in general I would recommend you to do this. Also, one useful trick is just using aliases. So aliases allow you to have like shortcuts for longer commands. For example, when I want to source my virtual environment here, I would need to type in source virtual environment dev bin activate. But instead now when I add this to my bash RC, I can just write venv_dev and I load my virtual environment using this. So to the next part, as a summary, so Python packages can be installed locally or globally. They can be installed only for your current user or across users on your system, which also makes a difference. If you have a hard time installing things here, just go and read the documentation of the package manager. The link that I put down previously is really exhaustive and gives you a good overview. Also, you can always talk to your supervisors regarding installation problems. And one of the tips that I just want to highlight again is just programming is basically knowing when and where to search for information. So this was told by one of my teammates at a PLR project like 2 or 3 years ago, and I think he was fully right. So some tips here. Don't spend too much time just going on YouTube or reading blog posts. Instead, just use the command line interface as your first help point. If this then doesn't work, just go ahead, go to the official documentations and check out which information is put down. Usually the people that develop those packages are very careful with which information they want to share with you, and that's usually information that you need. Always make sure that when you go to these documentation websites, especially for packages, that the version of your package matches the version of the documentation. So for example, in PyTorch you can click on this small triangle and then select the correct version. The same holds for OpenCV, which can be a lot of pain if you don't know about it. And then also as a last tip, don't be too afraid to read just the source code, because very often if it's a fully Python package you can just go into a source code and figure out what's actually going on and what causes the error. Okay, so with this, next problem where people typically have troubles is installing CUDA or Torch, and there's a few things that you need to know to get it right. So the good thing to know is that Torch comes with its own CUDA toolkit. So per default you don't need to install CUDA toolkit on your system, you can just pip install Torch. You only need the CUDA toolkit if you need to compile libraries from scratch. So, and also keep in mind what you need to figure out, that there's a graphics card driver version that you need to have running, such that you have kind of the CUDA is enabled, but it's not the same as your CUDA toolkit version. So here's a few tips. So if you need to install now CUDA on your system, you should use the latest version that is used to compile Torch by default. So if you look at this website that you're familiar with, you can see that the stable version of PyTorch, and that's today 2.2.1, is built with the CUDA version 2.1. So you should also install this version of CUDA on your system if you need to, such that you don't cause any version conflicts further down the road in your project. If you need older versions of Torch, for example, there's pre-built binaries available that you can easily make use of. So there's this link there, and then you can easily install it with pip, which is very helpful to know. Now I already teased you with using Torch as being a very popular machine learning framework that is very popular in research. There's also certain other frameworks. For example, there's TensorFlow that is mostly developed and maintained by Google. It's very well developed, it's very popular, and it's specifically popular in industry and production, I would say. Then there's PyTorch, which is mostly maintained by Meta. It's highly popular in research. I would say it's the most popular within research at the moment. So most papers are published with it. And the third alternative that I want to show is JAX, which is kind of this uprising machine learning framework that is quite kind of new. It follows a functional programming paradigm. So it's a little bit different to TensorFlow or PyTorch right now. And it gains a lot of traction in the research community, but still the community is quite a bit smaller than for PyTorch. But so if I have to give you a recommendation, I would recommend you to just choose one of those three, depending on your problem set, but most likely PyTorch will already do the trick, or you might be already like constrained by the code base that you're building up on. So then the next part I want to quickly go over is when to use an IDE and what is a Jupyter Notebook and when to use it. So with IDEs, they are typically very useful if you have larger programs, projects that you want to be working on, if you need advanced debugging and, for example, version control. For anything else that is more like a throwaway script that you just write for a quick idea or prototyping or visualization, the Jupyter Notebook is perfect. Or you want to share a bug with a person, just sending one file with a Jupyter Notebook is very easy to communicate. So choose wisely, but for this project I would recommend you just use the IDE, given that you will spend multiple months working on this. Then which IDE to use? I already, here again, spoiled you. So I would use Visual Studio Code in general. I think I'm very happy, it's very productive, it's very popular. Other people in the lab use, for example, PyCharm, where they also work fine with it. And then if you're very exotic, you can use NeoVim. But generally, I would just advise you, if you not have yet a favorite IDE, just go with Visual Studio Code. One of the important parts that I would tell you and really highlight here is invest a minimum of 2 to 4 hours of understanding your IDE. Really figure out what the IDE has to offer you, because this will make your life so much easier down the road in the project. So this is really well invested time. Then, for example, if we look at Visual Studio Code, there are certain tools that just allows you per default. So you can search the files, you have different files that you can open. You have version control that's already integrated. There's a debugger that you can use, and you can make use of various extensions that help you throughout your development process. So given that I don't have enough time to explain everything about it, just if you are not familiar yet, check out those two links. There's people that really explain this in nice videos and give you a quick start into using Visual Studio Code. Really make sure that you understand what's going on and what your IDE can provide for you. So as the next part, I would like to talk a little bit about debugging. So debugging is very important. So nobody writes perfect code, so your code will always fail at a certain point. And so here, what typically people would do is just run your Python script with Python 3 train.py, and then we get here this error in this return statement where we want to add together a and a variable c, and we cannot concatenate a string and an int. So I would highlight that you should nearly never see such an error in your command line, because I would recommend you per default to just run your code in a debugger if you have an IDE available. So for example, in the debugger, we now exactly get the line highlighted where the error occurs. Also, we can just go in and inspect here in this debugging console what is actually the content of those two variables. So we can print out a and we can print out c. We can see here on the top left the local variables that are available within the current scope, so that we can see that we have A and C being available. We can also see the call stack, where we know that we are kind of calling this test.py here, and then within it we run this method called getting started, and we can switch between those call stacks. We also see that we can add breakpoints and other things that help us to debug. So just keep this in mind and really make use of those tools that are available for you and are really well developed within the Python framework. Then also a quick example, just make use of the property that in Python basically all objects or everything that you have is basically an object. So you can, for example, call this dir function on it, and then it tells you, for example, which functions you can now use to call. So for example, we see this for this string that we're calling here, and you can see which functions are available for a string. So I didn't know, for example, that there's like this function called clear or extend within a string. So it's very easy when you have a breakpoint that you can just call this dir command, and then you see what an object offers you. It's a very good way to debug and to inspect if someone just gives you back a variable, what it is actually doing or what you can do with it. Then we now switch a little bit the scope. So I want to talk about this problem of reproducibility. And what I want to say is that reproducibility is very hard. And it's basically reproducibility in the sense that your code, your data, your configurations, and your environment need to be all reproducible. And for this, it's not only about choosing the right tools, but it's basically a mindset that you should have. So you need to start your project in the mind when you run a training run that you might want to rerun it like 3 or 4 months later. And how you can achieve this is very essential, such that you get everything right. So just take this reproducibility as a mindset, and it's basically up to you if you achieve it or not. So let's at first talk about your code. So what is very important and very simple is just that you need to seed everything when you run experiments, such that you run them with the same random seed, which is very simple, but you also need to get this right. So always read the packages that you're using your documentation for it. For example, in PyTorch you have this documentation about randomness, and that explains you exactly which kind of seeds you need to set and how to set them, such that things are as reproducible as they can get. And then further, what is like best practices, such that your code is always like up to date. You can check in different versions of your code each time when you run an experiment, and then give it a correct commit message, and then you can, for example, store this commit address with your experiment. So this might be one version to do it. There's different versions that we will talk about. I'm not doing this, or I would not recommend it, but it's one version that some people are using. Another option is each time when you run your code, simply copy over all your files that are actually your code to the experiment folder. Typically your files of code are very small, so we are talking about a few hundred kilobytes that you need to copy over to your experiment result folder. So here in these lines of code, I, for example, get all my Python files and all my YAML files, which would be the configurations, and just copy them then over to my experiment folder that I create for this experiment. You can also, instead of just copying them over to a local folder, what is even more recommendable, uploading them to an online logger framework, where, for example, weights and biases or Neptune AI can help you out, and you just can upload all of your code online. And then you have this stored there on a database and can always go back when you see your results of an experiment. You know with which code and which configuration the code was executed. Okay, then talking about configurations here, there's a problem that you should always store your code and your configuration together. Because what typically happens is your code is evolving and your configurations are changing, and the configurations that you once used are not compatible with all versions of your code. So just ensure to always save the code as well as your configuration files for each experiment. This is something that I was not told and did a long time wrong, that led to a lot of errors and headache in hindsight. Okay, so for configurations, there is multiple options that you can follow. But the first thing is just try to make sure that you only have a single source of configuration. That makes your life way easier and is very easy to share and to understand for other people if there's only a single source of these configurations that are used for your code and not at different places. Then keep your configuration files as simple as possible. So simplicity is really the key here. Don't overcomplicate structures for configuration files. Keep it as simple as you can. Then ensure that your configurations cannot cause these silent errors. For example, you need to change your network, but also you need to change your loss function together. So if this just runs, but then produces the wrong result, and you also need to make sure that a specific configuration works with or a specific loss function works with a specific network, you might want to have this as a verification step that you just add to your program. So kind of making verification beyond just type checking of your configuration. Then I would recommend you to use human readable formats for your configurations. So YAMLs or JSONs are recommended. I would even recommend YAML over JSONs, given that you can add comments to your configuration files. These are, I think, the two most popular markup languages that you can use for these things. Then, looking at these configurations, it's basically a trade-off between the functionality and complexity. So obviously, more complex frameworks for configuring stuff allow you to add more functionality, but then the complexity increases and might get more complicated to understand for a person that picks up your code. So kind of choose wisely. There's 4 different things that I want to quickly tell you that you can use. The simplest one is the command line interface, where you simply pass a few arguments to your command line interface, and you can do type verification, but that's already it. Then you can use data classes, where you can give your configuration that goes in specific types, and then your configuration is basically part of your code. There's also something called Omega configuration, where you also have those type configs, but you have simple tools to storing them and loading them and extending configurations in certain ways, which is not too bad. And lastly, there's like a framework that's called like Hydra. It's specifically designed for machine learning projects that allows you to have multiple configuration files. It allows for automatic instantiation of objects and configurations and can be very useful. So if you think about it from left to right, the complexity increases, but also the functionality increases. So I would also recommend you here to choose wisely, but for most projects, I would nearly say like go all the way to the left with the command line interface or Hydra, but also data classes and Omega configurations can be very useful and handy tools to know how to use them. Then jumping to your environment that we also need to reproduce. This is a little bit more tricky, but it's also obviously often therefore ignored, that people don't care really about the environment. So best practices might be already that you can store your packages that you're running for your Python environment each time you run your code. So you take basically the output of pip_read_list and just write it all to always to a file each time you run your code. Such that you just know, okay, I use these Python packages in this version to run the code, and it ran with these specific versions of the packages. Then obviously there's tools like virtualization or containerization, for example like Docker, that can help you also to make it even more reproducible, but I would say this is the cherry on top for this project, and if you're not familiar with it, it might be also a lot of overhead. So you need to kind of get it right between like making your environment reproducible and being able and quick to move and develop within your project. Then also one thing that is very often ignored is data sets, and that is actually pretty crucial to get right. So here with the data sets, it's as follows. You often will find yourself that you have to work with multiple data sets, and these data sets can come in different formats, and this can be actually quite complicated to manage. And what I would recommend you, even though you start out using a single data set for your project, always assume that your data might change, because you might want to change the test train split, you want to add certain validation data. So if you have this in mind, you already figure out a system on how to versionize your data sets. So similar to how you versionize your code, you should versionize your data sets. Therefore add these versions. And here comes now a tip. For example, here we are doing SLAM, and we would like to run our code on all of those data sets that are publicly available. Now these data sets come all in different formats. So what I would recommend you to do is convert all of those data sets once into a common or your preferred format. And you just convert it once. After you convert it, you verify that this conversion is done correctly by visualizing everything, and then you know you're kind of good to work with it. And that allows you that you don't need to maintain different adapters or data loaders for each data set, which is very error prone, because then you just need to have like a single data loader that is the same for all the data sets, and you just need to change the path. I think that's a very simple trick, very easy to follow, and that will potentially also save you a lot of time if you have to work with multiple data sets. Then also what I want to tell you quickly about is that machine learning is basically one pretty big scaling problem, because we want to train very deep and very complex models. We require scale. And just as an overview, what might be a bottleneck is basically everything. So your GPU throughput, your memory, your limitations in terms of CPU, your limitations in terms of your RAM memory that you have available, or your storage, disk space capacity, as well as your input outputs for data loading or your network. So one of the important things is that you need to be able to identify those problems. So the first thing that you should do, always if you run your code, even if it runs fast, just go ahead and measure things. So figure out the basic things, what you can measure and how you measure. And the tools, or what, not the tools yet, but so here it's also important to understand basically in terms of those scaling problems, what problems you might run into. Are you on a workstation or are you on a cluster? Do you need to use the network to get your data? And then when you identify those bottlenecks by measuring, also understand which gains you can get. And all of these problems in terms of scaling is basically a trade-off between your time, the complexity it takes to make the code faster, and then the actual runtime of your program, how much time you save or how much money you can save by making your code work faster. So it's basically something you need to get right, because your time is also quite valuable. So a little bit about the tools that you can use to understand those scaling problems. One tool is to just understand your file sizes and storage. Then you can go ahead and use something like HTOP to manage, to monitor your CPU usage, but also tools like NVIDIA SMI or NVTOP show you your GPU utilization or your VRAM usage. They are good indicators if your GPU is running at the full rate it can. Based on these tools, you can then also go and start and benchmarking the code. And here I brought you an example where we would like to time the forward pass it takes for a model to forward this batch of data through a big neural network. And I would like to ask you here quickly, if you have like this problem, what can go wrong? What goes wrong is that we are using here this timing library, and this timing library takes the time before executing the model and after basically passing the model through the network. And this time that is printed here will be most likely wrong because we are running on GPU. So you should understand the difference between running on CPU and GPU. What you instead would like to do is use the torch provided functionality for timing by start and stopping those events. Because in the background, when you run your model, basically the data is handed over to the GPU and you just asynchronously use your GPU. That doesn't mean that your result needs to be ready by the time in the previous code we have reached the timing statement here in the last line to compute the delta, because the GPU might be still processing, but given that the result is not needed yet, we can just step forward within Python. So that's a little bit complicated to understand what's going on. I would highly recommend you just read exactly what you're doing, and I did a small package on how to do this very simple, that you can use this GPU timer or the CPU timer. So feel free to check this out and use it, but otherwise just always read how you time things correctly when you have to do it, given a certain library. Then also for like the scaling problems in terms of data sets, you should understand how many files you have and what's the size of your data set. Then you should understand usually if your data fits inside the VRAM, then you should just put it inside directly into the VRAM of your GPU, which is the fastest memory, given that your networks will most likely also live on the GPU. If you can fit the data set inside your RAM, then just put it inside your RAM, and it's also very quickly to load over to the GPU, and you most likely won't have a bottleneck. If you have a lot of different files, you should also think about which file format you want to use for storing the data, and also what's the best practices in terms of loading those files from the disk, if it's better to have a lot of small files or one big file. So these are things where you really need to go into detail, and you can talk to your supervisors to understand more what's the best practices in the field. So here again, there's a tip: just communicate these design considerations that you did or these design choices with your supervisors. Most likely they already have a lot of advice and experience using those tools and can just let you know if you're doing the right thing or the wrong thing. So with this, I'm already finished with the lecture and would like to thank you all for your time and attention.